Hello. So today we will be learning about data structure, an interesting data structure called heap. Now, before we start, let's ask what is a data structure. So data structure is a special way of storing data such that certain operations can become easier. For example, we have already seen data structures like array or linked list in which the idea is to store the data in a particular way, and like for example in the case of array, finding an element is very easy, but in a linked list adding or removing of elements is very easy, right. Similarly, there is another kind of data structure called binary trees, and this is a very important uh, data structure. So what is a binary tree? So a tree is basically a and graph like this, right, in which you have some root and you have these children, and it goes on like this. In general, a tree, a root or a node, so these are called the nodes, right. And so if this one is the, if I name number A and number B and number C, say B and C are the children of A, and likewise A is called the parent of B and C. And also one more thing is that in a tree in general, this A or any node for that matter can have more than one, more than two children. But we are interested in binary trees. Binary trees are things in which every node has at most two children. So this is an example of a binary tree, right. So every node has at most two children, and that's about it. And then we have the, at the end we have the last ones which have no children, and these are called the leaves, right. Now one way of storing data is to store this data on the nodes, and in such that some kind of a rule is preserved. Say for example, if I want to store the numbers 1, 5, 7, 9, 2, 3, I could have stored it in a way that, okay, I would like to store the number, I would like to store it in a binary tree. So number 7 will be here, number 5 will be here, number 1 will be here, number 9 will be here, number 2 will be here, and number 3 will be here. So this is a way of storing these numbers, these numbers in this. But as you can see, this is a pretty ad hoc way of putting these numbers. Is there some other nice way of putting the numbers? Say one way we can think of doing a number is by putting that, okay, I would put a number, okay, say like I put a number here 7, on the left hand side will always be something that is less than the that number. So the left child is always less than the node, and the right child is always more than the, or more than or equal to the node. Now this is one way or one rule that we can follow while storing the numbers in a tree. So this is a standard thing, this is used in the binary tree, and you guys can go and check what advantages does this particular thing give. Now a heap is exactly something like that. So heap has a particular rule. So let's try to see what does the heap rules is. So, heap stores this data, which is basically numbers, in the nodes of a binary tree such that it satisfies two different rules. First rule is that the number on any node has to be less than all the numbers in the subtree. Okay. So, if I go back, by the way, I should say that this, if this is the node that we are talking about, then this subtree is basically everything here, okay, or rather maybe this is not the right way to say it. So, it has two subtrees, it has this subtree and this subtree, the left subtree and the right subtree. Okay. So, in the case of heap, it is, the rule is that the number on any node has to be less than all the nodes in the subtree, or rather I would say it is on the subtrees, both the left and right subtrees. And also I need that the tree is almost balanced. Now, what does it mean by that? Let us go back to the picture that we had drawn earlier. Note that this is not exactly balanced. Why? Because I could have maybe removed these two nodes and instead put up here, and that would have been balanced. Balanced meaning that the leaves, all of them are almost in the same layer. Earlier what was the case is that it was not the same layer. Now, we can have some more stuff, like for example, what happens if we add one more? Is this balanced? Now, technically this is balanced because all the leaves are either in this layer or in this layer, but we would like it to be balanced from a particular direction. So, in that case I would like it to be in the left side. So, the idea is that it is balanced, meaning if whenever new element comes or when the number of edges goes up, number of nodes goes up, it should get added to the leftmost node possible. Okay, I am not giving you the formal description of that, you can write the formal description yourselves. So, a node, so a tree is almost balanced, and I would say that from left. Okay. Now, this is what is known as the. Now, what are the advantages of this? Let me say, for example, I want to store this number 1, 3, 5, 7, 9, 10, 11. Now, I can store anything. Now, note that I have to store it in a place such that whatever I store here, right, whatever I store here has to be less than everything here or everything here. So, in short, this number must be the minimum of this set, right. So, it has to be the minimum, hence it has to be 1. Now, once I have this one, I can partition these two sets, this remaining set, say 3 to 7 in whatever way I want, and I can store them in this left and right nodes in whatever way. Say I decide to put in this left node, I would put the numbers 3, 7 and 10, and here I will put the numbers 5, 9 and 11. So, I can put here by the same argument, this node must have the minimum of these 3. So, it should have to be 3, and in that case I can have this 7 and 10 over here. And similarly here it has to be 5 and I have 9 and 11, 9 and oh, see, I don't have 8, so oh, sorry, this is 10, so this has to be 11. Yeah, so this is a heap. Okay, I can erase this. So this is an example of this data stored in a heap, right? So if I have another number, say for example, I have the number 12 or 13. Now I can put it in such a way, where do I put it? I can put it here, because note that I cannot put it here, I cannot put it here or here or here. So in that case the heap is not sorted, sorry, heap is not balanced. But if I put it here, then the heap is balanced, and in that case we can put it there. So you have a set of numbers, and this is how you store the elements in a heap. So to look at it again, the numbers you can store it in whatever way you want, but all you have to remember is to satisfy these two property, that number on any node has to be less than the number in the subtrees, and secondly the tree must be almost balanced from the left. Now let us see what are the advantages of this. What are the advantages of this heap store? Oh, rather, okay, before I go into it, let us think about how is this heap stored. So let me draw it once again. Okay, so I have this number 1, 3, 7, 5, 8, 9, 10, 11, 6, right. So note that this is a heap, it satisfies all the properties. Now how can I store this heap? So this is a very interesting thing. I have told it very abstractly, this heap is this tree and all of that, but how do you store it? So do you store it as a linked list, or do you store it as a array, or how? So the trick here is actually to store it as an array. Okay, and it's a very interesting thing to look at. So if I number this nodes in, so this is the first array, first node, second, third, fourth, fifth, sixth, seventh, eighth and ninth node. You will see how I marked it. It is from the left to right in the same layer. In that case, what is stored in the, so this one will be stored in the, so this number, since it is number 1, it is stored in the first. This is number 2, so this has to be stored in 3. This is number 3, so this must be stored in here. Similarly, at the 4th place it has to be 5, 5th place it is 8, 6th place 9, 7th place 10, 8th place 11 and 9th place 6. So I have stored it in a way. Note that this is a one-to-one correspondence, right? You can understand, once you are given an array, you can come back and produce the heap, and similarly if it is stored in a heap, then you can come and produce the array. But there is more to it. What is the left child? Where is the left child of a node? So if the node I, if I am considering the node I, whatever that node I, oh, so I mean, I don't mean node I, not the element I, but the node numbered I. Say I am interested in the node number this one 2. Where is the left child of the node number 2 stored? It is stored in number 4, right? And its right child is stored in number 5. Similarly, if the number is 3, if the node child is 3, then the left child is stored in number 6 and the right child is stored in number 7. Actually, if you can see it, that the left child is always stored at number 2i's I and the right child is at 2i's I plus 1 location. So, this is kind of very important, like I am interested in, as I want to know, I am in node 1, so which is here, fine. Now, I say that, oh, I want to go to its right child. How do I go to the right child? It is 1, that means the right child has to be 2 times 1, that means 2, 2 times plus 1, right, which is 3. So, the right child must be in the number 3. So, I go to the third location, I find, oh, the thing that is stored in the right child of 1 is number 7. So, here realize that this whatever has been written in red are the indices of the nodes, and whatever has been written in black, these are the numbers contained or stored in that node. So, in short, a heap is nothing but an array with a particular structure. A heap is same as an array is same as a heap, but it has some very nice structure. So, it is not any array does not form a heap, right, because heap must satisfy these two properties. For example, in the heap, the first element must be the minimum element, right, and so on and so forth. Good. So, a heap is stored in such a way that it is stored in an array such that the left child is stored at the 2ith location and the right child is stored in 2i plus 1th location, right. Now, okay, we have described a heap and I have described how it is stored in an array, but the most important question is that what are the operations that make heap useful? And this is kind of very interesting. So, let me just first draw a heap. So, I have a number 1, 3, 7, 8, 9, 10, 11, 20, 18, 30, say something like this. Now, what happens if I want to recall that there are two important things that one needs to do. One needs to insert and one needs to delete. These are the two very important operations that is required for any data structure. Because you want to store data, and of course you might want to remove some stuff from the data, or you might want to include some stuff from the data. Now, how do I do it? Say I have the number 6 that I want to insert. So, I want to insert number 6. How do I do it? So, the way to do it is, say we want to insert the number 6. Note that the one important thing that we have to ensure is that the heap is balanced. So, that means once I add this number 6, it has to be something must be added here. So, what I do is I add this number 6 over here. Okay, so at least the heap is balanced. But it might be balanced, but that is not very useful, right? So, what do we do now? So, now the way to do it is that, see, the problem is that 6, look at this parent of 6. The parent of 6 is 9 and 6 is less than 9. So, that means this should not be the case. So, what do? I swap these two. So, I take the 6 over here and 9 over here. And now I see that, okay, the 6 has gone up. Now I look at 6 with this parent. Oh wow, see, 6 is bigger than 3. So, we do not need to swap here, right. So, 6 therefore is bigger than 3, so it is fine. The only other place a problem might occur is 6 with its left child, because it has entered it from the right child. But can it happen? See, before 6 came, it was 9 was here, and 9 was anyway lesser than 13, right. 9 was lesser than both its left and right child. So, 6 was anyway is less than 9. So, 6 must be less than its left and right child now. So, it does not have to look below. So, whenever we are putting an element, we might have to move that element upward, but we do not have to ever look down. So, in short, what I mean is that you can insert an element in the heap with just something like you just have to go and flip it all along the path. And what is the length of the path that are there? What is the maximum path that you might have to go? It is just the depth of the tree, right? And which is order log n. Right. Now, the another thing is that, of course, what about delete? So, now I want to say do something like I want to delete number 3. So, how do we do it? So, of course, first of all I have to delete it, there is no question about that. But once I delete it, there is a vacuum over here. And how do you take care of that? Again, the issue is that we have to ensure that the whole thing remains balanced, right? And this is something very important. So, what we can do is that, so we can now just try to do this exactly the opposite of what was did last time, which is that we look at the one that is at the end and remove this one and put it here. So, we can remove this 9 and put the 9 over here. Now, note that I will just change that 9 to something else, the colored 9. Note that this 9 now, of course, has a problem. The tree structure is exactly what it should be, right? The only issue is that it has to go down properly, right? So, what we do is that we look at what does, so this 9 now has a problem. This is not less than 8 and not less than 6. So, we need to flip it, right, and it really does not matter which way we flip. We can flip 9 to 8 or 9 to 6, but again whatever we do, it has to be different, right. So, what we can do is that out of these 3, we can look at the one which is the smallest, and in this case it is the 6, and we swap 9 with this number 6. So, we get 6 over here and 9 over here. Note that the 6 is now the smallest. 6 is anyway less than 1 because 6 was in the subtree of 1, and 6 is smaller than 8. So, there is no issue over here, right. And you have this 9, and this 9 also now is going in below it. So, all I need to look at now is what happens when I look at 9 with its neighbors. And as we see here, we do not have to have any problem, and so we can be fine. So, again, when we delete something, what we do? We delete, then we take the element from the last node in the heap and put it there and slowly bubble it down, right. So, this way you can do it again. In this, the total number of swaps that you need to do is just the depth of the node, it is log n. So, I have not given you the full details of how the operations of insert and delete happens, but I hope that the ideas are fine. So, I would like you guys to go, I would like to write down formally the insert and delete operations. How do you do it in the case of heap? And also in the standard heap terminology, there is this insert, there is a delete, and there is the last one which is basically nothing but a delete, but it says extract mean. By the way, whatever we have defined till now is what is known as the mean heap. Mean heap because you stored the minimum, I mean the node is smaller than the other 2. If we have defined just the opposite, that the element stored in the node is bigger than the subtrees, then we get the opposite, which is called the max heap. We have defined here the mean heap, and in the case of mean heap, there is this thing called the extract mean, which means that it removes the topmost element of that, and it basically have to do the whole thing. Okay. So, I would like you guys to go and write down formally the definition of heap, then the pseudocodes for insert and pseudocodes of delete and pseudocode of exert mean. Now, with all these operations on heap done, it is important to ask, why do we even think about applying or coming up with a new data structure? So, I want you guys to see how you can use heap data structure to obtain a sorting algorithm. I want you to design a sorting algorithm that uses this heap data structure, analyze its worst case running time, its space complexity, and ask all the other properties of this particular sorting algorithm.